In this video, uh, I'll be solving some torque problem. So just to get started, here's the sample problem. So this is a rigid object of any shape, and this is acted upon by two forces: F1 at R1 distance, F2 at R2 distance at these angles. So uh, it's just acting. What's the net torque acting on this rigid object? So just to give you a formula, so the vector torque is just R cross F, right? But its magnitude, that's what we need, is RF sine theta, where theta is the angle between force and this position vector, right? And to find the direction, you have to use right hand rule. And let's take a simple example. So for example, uh, uh, this is the rod. Say you apply force right here, and let's say it produces torque like this, right? This is the point of rotation. If the torque produces counterclockwise rotation, then that is positive. Okay, counterclockwise torque is positive. Why? Because from our rule, right hand rule, R cross F, so thumb is the answer. Thumb is the torque direction, right? So positive. So similarly, if the torque produces, however, if the torque produces, let's say you apply here, right, and this will produce clockwise rotation, and then in that case torque will be negative. So keep that in mind. Counterclockwise is positive torque, clockwise is negative torque. So here we're going to find the net torque. So the magnitude of the net torque is, so R1 F1 sine theta 1. You have to decide whether it is positive or negative. So this R1 F1, so it is trying to produce torque like this, right? Clockwise counterclockwise rotation. This is counterclockwise, so it's positive. And whereas F2 is will produce clockwise rotation. See, clockwise, so it's negative. So negative R2 F2 sine theta 2. And after that, just plug all the numbers. So R1 is 1.3, F1 is 4.2 newtons, sine of 75 degree, minus R2 is 2.15 meters, F2 is 4.9 newtons, sine of 60 degree. So that's your net torque max. So net torque magnitude, if you do this calculation, you're going to get negative 3.85. It could be negative or positive. So here you get negative torque. Okay, so that's your negative. Simply means now this rigid body will rotate, eventually rotate clockwise. So that's it. So next problem is, let me show you one problem with you know, cross product. Okay, so if the force and position vectors are given in terms of components, unit vectors, so how do you find the net torque? So again, so here R, which is the position vector, right, which is where the force is applied from the origin, is negative. I'm just gonna write down the magnitudes, I mean without the units, 2j, right? And there's no z component. So similarly, force is applied only along z direction, right? Because there's only k hat. So 0I plus 0j plus 3 newtons in z direction. So force is applied only along the z direction. So then how do you find the net torque? The vector torque is R cross F. And this can be, right, written in terms of determinant form as we discussed in the previous lecture, I, J, K, and then you first need to put the components of the position, not F. First comes, the position. So negative 2 to 0, and then you put the components of force here finally 0 0 3, and then you apply the rules for the determinant, right? And that's how you open the so I, right, you do this as you learn from math, this minus that. So 2 times 3 is 6 minus 0 plus j will go opposite. So this 0 minus minus 6, 0 minus negative 6 plus k will 0 minus 0, so it will go. So your net torque in vector form, right, in ijk unit vector form is this 6j. Alright, that's your answer. Okay, it has same components. And if you want to find the magnitude of this torque, right, magnitude of this torque, then it's gonna be this. So it's going to be 8.5 newtons meter is the unit. So that's how you, if the R and F are given in components form in IJK, you can just use the determinant R cross F and determinant. Okay. Okay, let's move on. So next is some simple examples. So this, you apply force. So this is a wrench with some jitter bar, right? To increase the torque, you have to add some extra length. That's what, and then you're trying to unscrew something. So you apply 900 Newton force here at the end of this wrench, which is, so this is your R, this is your position vector R. And remember, it's acting the net torque magnitude RF sine theta. So what is this theta? Theta is the angle between R and F, right? Angle between R and F, not that one. So this is 90 minus 19, so 71 degree. That's what you need. So the position vector magnitude is 0.8, force is 900 newtons, sine of 71, not 19. So the magnitude of the torque is going to be so I have the answer for that is, if you do that, is going to be 681 newtons meter. Okay, and its direction is, so let's see, just use common sense. It's trying to produce a rotation like this, right? This is counterclockwise, and remember counterclockwise is positive, so it's positive torque. Okay, all right. So similarly, pretty similar. So here this bar is acted upon by two forces, F1 and F2. This is making 90 degree force, this is making 30 degree angle, and it's acting the net torque, acting net torque about this pivot point. This is the pivot point. So net torque magnitude, this is tau, is again R1 F1 sine of 90 degree, right? And positive negative you have to decide depending on the clockwise or counterclockwise. So this is producing torque like that, that's counterclockwise, positive. And the next torque is torque produced by the F2, which is trying to produce, oh no, I'm sorry, this is negative, this is clockwise, right? This is clockwise. And the F2 however will try to produce torque in this direction. This is counterclockwise, right? This F2 is trying to produce counterclockwise torque rotation, so that torque is positive torque. Counterclockwise is positive. So just put all the numbers. So R1 is this whole distance 5, F1 is 8 newtons, sine 90 is 1, plus R2 is this, which is 2 meters, F2 is 12 newtons, and sine of 30 degree. So if you do that, the net torque, the magnitude of the net torque about this pivot point will be 28 newtons meter. Okay, and what's the direction? So direction, so it came out positive, so that means this rod will rotate counterclockwise, so its direction is positive. That's why you figure out. Okay, so pretty similar. Okay, next is I will be solving. So I will just give you some idea actually. So this disk is acted by three different forces acting at different. So and I will just give you the basic idea. First, you need to figure out. So let's call F1, F2, F3, right? So this is R1. You have to find. This is R2, R3. So R1, R2, R3 are all equal 0.35, and do the exactly same. So you just need to figure out net torque magnitude is R1 F1 sine force is 0 degree, right? So it doesn't produce any torque. And second one is, so it's trying to produce clockwise torque, so negative R2 F2 sine of 40 degree. And third one is it's making 90 degree angle, so but it's actually counterclockwise. So counterclockwise means positive R3 F3 sine of 90 degree. Okay, so find that out. Just plug all the numbers in. Alright, so let's move on. Now I'm gonna solve some problems where you apply different concepts, two different concepts, rotational kinematics with torque. So here are two problems. I will solve both of them. So here's the example. So the first problem is a 250 gram 24 centimeter diameter plastic disc is spun on an axle through its center by electric motor. What torque must the motor supply to take the disc from 0 to 1500 rpm in 4.2 seconds, right? So the main idea here is it's asking what torque you need, what torque the motor need. Okay, the motor has to apply torque to rotate so that it goes from 0 to 1500 rpm. Rpm is revolutions per minute in 4.2 seconds, right? So I will show you what you need to calculate the torque. Torque is, remember, in Newton's second law in rotational form is torque is I times alpha. Okay, you can just compare, you don't need to memorize this. Compare with regular Newton's second law. Remember, the Newton's second law is mass times acceleration, right? So that means the vectors force and torque are similar. Alpha is in rotational kinematics, A is in translational motion. And remember this, right? That's how you compare. The moment of inertia is plays same as mass. So these are both Newton's second law. This is our regular Newton's second law in translational motion. This is the Newton's second law in rotational dynamics, rotational motion. So what you need I and alpha. So I, for this is the disk, circular disk, is given on the table is 1/2 mr square. Okay, so that you can calculate. Right, so which is you can calculate that, right? And so how do you find alpha, right? I you can calculate using this formula for moment of inertia for a circular disk. Alpha you need rotational kinematics. You can use rotational kinematics, which we discussed in the very beginning, right? Our first topic, to find alpha first. So remember, your omega initial is 0. Omega final is 1500 rpm. But it's revolution per, you have to convert into radians per second, standard unit of omega. So you have to do like this, 1500 revolutions per minute. So you have to multiply by, one revolution has 2 pi revolutions, divided by 2 pi over per minute. 1 minute has 360 2 pi, I'm sorry, just 60. 1 minute has 60 seconds. So that's how you convert rpm, which is revolutions per minute, to radians per second. So omega final, if you do this, is going to 157 radians per second. and you're given the time, right, for 4.2. So then you can find alpha just by using the rotational kinematics, which we did in the very beginning. Initial plus alpha t, right? So then your alpha is omega final minus omega initial divided by time. So final is 157, initial 0, time is 4.2 seconds. So that's gonna give you 34.4 radians per second. So that's what you need. So so I'm just gonna do it here. So finally the torque produced by the motor, right, is I times alpha. So I is 1/2, mass of the motor is 0.25 kilogram, and the diameter is 24 centimeters. So radius is 12 centimeter. So 0.12 square times alpha is 34.4. So that's gonna be your torque produced by the motor. So motor is uh, you know motor produces that much torque. So if you do that, 0.0, I'm sorry, this is alpha is 37.4 actually, 0.0673 newtons meter. So that's your final, very final answer. Okay, let me show you one more very last problem for this lecture. So here's the question. If you lift the front wheel of a poorly maintained bicycle off the ground and then start to spin it at initially 0.45 revolutions per second, it's not radians per second, it's revolutions per second. Friction in the bearings causes the wheel to stop in 12 seconds, right? Finally it stops. If the moment of inertia of the wheel is about its axle is this, and what is the magnitude of the frictional torque produced by the friction? So it's the same thing, right? So it's acting the frictional torque produced by the friction. And again, this is I times alpha. I is given. So I for the bicycle wheel is 0.30, its unit is kilogram meter square. That's given to you. And what you need to find is alpha, which is the, now in this case, angular deceleration, right, is because it's slowing down. So let's do that again, just like before. So omega I, it is spinning at 0.45 revolutions per second, but you must convert into radians per second. So how to do that? Just multiply by 2 pi, because one revolution has 2 pi, right? So alpha is omega I is 2.83 radians per second. What would be omega final? So of course it's 0, because it's finally it stops, the bicycle will stop. Then again, using the rotational kinematics, right, you can solve for alpha. Alpha is final minus omega initial divided by time. So omega is 0, omega initial is 2.83, so it took 12-second time to stop. So alpha will be negative 0.24 radians per second square. So what's the torque produced by the friction? So torque produced by friction, frictional torque, is then I alpha. So I is 0.30 given, so negative 0.24 is alpha. So friction torque finally is given by negative 0.07 newtons meter. So that's your final answer. Okay, so negative simply means is a frictional torque produced by friction. Okay, that's all for today, and this might help you in doing the quiz problem.